excited about that. You get a chance to show faculty what you've been working on. Do good on all your tests. All right, you've been practicing a lot. So, a little housekeeping. First things, just a reminder, this week's lab, the copper analysis lab, we made, well, for each of you should have, you and your lab partner, 4 samples. 2 barium sulfate and 2 of the copper silicyldoxine complex, or compound, right? And so we've got those drying in our drawer. You'll weigh those next week, and then the lab will be due the following week, okay? So there is no lab due next week, all right? The second part of that is we will go ahead and start a new lab next week, which is the synthesis of esters. And so there's 2 steps in that one, where we make a small ester in a test tube, and then we're going to do a little bit more in-depth synthesis and analysis with vanillin. And so we're going to make a vanilla acetate, and we're going to start learning about spectroscopy and melting points and those types of things, how to do those techniques for synthesis. Cool? All right, so that, and then that lab is actually a 2-week lab, full 2 weeks. And so you'll do the synthesis the first week, and we'll do the analysis the second week. And that's saying we get our IR fixed because it's down right now. And the NMR is going to be a little bit crowded. So anyway, but that said, it's a 2-week lab. We're going to approach it as a 2-week lab. And so then that lab won't be due until the following week, and then we'll be back to 1-week labs. And so everything will align again. So there's at no point you'll have 2 labs due in 1 day. Okay, cool, you guys with me? That's by design, and it was also by design so you wouldn't have a lab due during midterm week in case you have a lot of tests. All right, cool. All right. 2 weeks, got that one. On campus web, just in case you're looking for that extra stuff, we started doing net ionic reactions, right? And so there are practice problems, and then there's a answer key to that, so you can have additional practice if you would like. All right, so you can go through and hone your skills. And is this helpful? I hope it is. I hope you choose to use that. I may change what this top part of this says, just to let you know. I may edit it and say something along the lines as the worksheet did on the last test, right? If you turn this in on test day, I might give you a little bit of reward for that, okay? Right? So you just have to write out all the reactions and show that you actually did the total and net reactions for each one. Cool? All right? You do that on a separate piece of paper and just staple them together. What do you think about that idea? Good idea? Yeah. So just trying to get you to work on those. Now, if you need help, all right, you're still struggling. Oops, I should have closed that. Let's see if it will open right back up. It did. If you're still struggling with oxidation numbers and those types of things, right? Don't forget that you can go back and work on practicing oxidation numbers, right? If you didn't do that to start with and it's killing you in this, then you can go back and work on this to help you learn how to assign oxidation numbers, okay? So that when you're breaking them down, you know what the charge is. And then you also would need to learn your polyatomic ions, okay? And so just throwing that out there. Cool? All right. So you can pick this stuff up and get better at it. All right. Any other housekeeping items? There's a quiz on the 23rd. All right, there'll be a test following that. And, oh, and I forgot to get my demo ready today. Well, I'll do that on Monday. I mentioned it to a student and they were going to help me with that, and then neither one of us followed through. I apologize. Gosh, I ruined Friday, didn't I? We'll work on this, okay? And, all right, this is actually where we were at. Yeah, we finished up on this slide. I just want to go over this one more time. And when you're doing net ionic equations, you're going to what? Consider the species that are available, right? Then what next? Exchange partners. That's pretty easy to do, isn't it? Okay. What goes with what? Cations go with anions, right? All right. Write and balance the equation. Write the complete ionic equation so you can show what's disassociated and what's not. Okay. And then take out what? The spectators and write a net ionic reaction. Now we're going to do the same thing with neutralization reactions. Now some of those have some more complex chemistry that goes with them. All right. But we need a definition, and this is the Bronsted definition. It's actually not as good a definition, in my opinion, as the Lewis definition. Okay? The Lewis definition includes all acids and bases, and it allows things like metals to behave as acids. Okay? And they do. Right now, we're going to use the Bronsted because it's more basic, and it considers that if you donate an H+, you're an acid. Okay, cool, you guys with me? So there's more than one definition of acid and base. Now, there's some cool things about them. Acids taste sour, hard, whatever the words you want to use. I mean, how many people have tried the sour gummies and all those fun things? Yeah, you guys know those are acids that you're, making those funny faces about. Citric acid is a very popular one, right? And so they just load up the entire outside with citric acid, and you stick that in your mouth and you just pucker, right? So it's amazing. All right. Substances who are in aqueous solutions, if I take litmus paper and put in there, then the litmus paper turns red. For some reason, that's in every definition of every general chemistry book. They turn litmus red. Okay? And they dissolve certain metals to form salts. Okay? They dissolve certain metals to form salts, and they react with bases or alkalis to form salts. Now, I'm going to put a quotation on salts. That they really do is they actually react with bases and form water. Okay? They make water. That's what they really make. And so this is a definition from your book. But the salt is actually in aqueous solution, so it makes ions, not salts.
So,
not unless you get rid of the water.
What are you saying they both form ions? Or?
React with bases or alkalis to form salts. Right? They form salt in water, and I put the salt in quotation because, well, the salt is dissolved as ions goes. All right, so base. Instead of donating a hydrogen ion, what does a base do? It donates an OH minus. Okay, now I may have to do some chemistry to do that, but ultimately it gives that hydroxide ion. And the hydroxide polyatomic ion is always charged what? -1. And when I take a +1 and put it with the -1, what do I get? 0 charge in water, right? The formation of water in neutralization reaction. You guys catch that? Yeah, in fact, we're going to prove that here in a minute. You guys with me? All right. So, bitter tasting, slippery solutions. Now, when we were down at the creek and we were using the buffer for the pH titration, I know there may be someone in here who actually held the buffer solution, and I told them if their fingers feel slippery, they should go to the creek and rinse their fingers. Why is that? It was a pH 10 buffer.
It's turning your acid or your oils into soap.
Yeah, it's turning your oils into soap. And so bases feel slippery because they take the triglycerides and they convert them into the salt of the fatty acid, and that salt of the fatty acid by definition is soap. You guys with me? Yeah, that's how I make soap, isn't it? I take lye. You guys ever heard of lye soap? Lye is a base. I put that in with my fat, and it cleaves the ester bond. Hey, we're going to make esters this week. You guys are going to see ester synthesis. Okay? You're going to take the carboxylic acids and turn them into a triglyceride, but we could easily remove that and turn it into soap. Okay? The reverse reaction. Hydration or dehydration. All right? So we'll look at that. But anyway, that's why it's slippery. And then bitter tasting, man, that is so true. Bases taste awful. Okay? Anybody like to drink sodium bicarbonate solutions, baking soda solutions? Like the flavor at all? No, nobody likes that. Okay? I don't think anyway. All right. Litmus paper turns blue instead of what? Red. Base is blue. That's why you can always remember it. Acid is red. Base is blue. Reacts with acids to form salts. Well, reacts with acids to form water. And so that's a book definition of salt. Substance produced by the reaction of an acid with a base, characterized by ionic bonds, relatively high melting points, electrical conductivity when melted or when in solution, and a crystalline structure when in the solid state. Okay, yeah?
So for testing purposes, you guys know that it forms salt?
I do, but I'm just telling you that I think that general chemistry books are wrong in that it makes water, the small molecule, covalently bonded, and the salt is an ion in solution most of the time. It does not precipitate. Does that make sense? And so I think that's misstated. It's for clarity for you guys, but I want you to know the real chemistry, right? So, but when you see that on a standardized test outside of this college, then realize that you better put it makes a salt, right? So, notice how I put it in quotations, salt. So if we're looking here and we're talking about this, I need you guys to use your solubility rules for me, okay? And so if I'm looking at, now you're not sure about this one. Well, actually we are. Where's hydrogen out on the periodic table? Alkali metals. It's placed there, isn't it? And so when I put that into water, it comes off as an H+, doesn't it? And we call that an acidic proton, right? We write it as, and I want to be very clear with this, why we call it that. All right, if I have H+, right, and it's not deuterium, it's actually the hydrogen ion, okay? Then what is present when this is in solution? Does that help? One proton, isn't it? There's no, if I'm looking at hydrogen, there's one proton, right? You guys with me? It can never be charged to anything but what? +1, because there's only one proton. If I have two protons, what am I? I'm helium. So now, when I'm in water and I'm dissolved and I'm H+ plus Cl-, you guys with me? Because those disassociate. Well, then we call this an acidic proton. You guys get that? You understand why that is now? Now, if I put an electron with this, right, it becomes H, and it would have one proton and one electron. Now, it's not happy with one electron, so it goes and finds another one and makes a bond with something else. You guys with me? Like carbon. And it makes a carbon-hydrogen bond, which has two electrons in it. Because everything wants two electrons, not one. Even hydrogen. Cool? So it can be like the noble gases. It wants to be like helium. Cool? Alright. So, what about sodium hydroxide? If I'm doing ions with that, is that soluble? Can I rewrite that as Na+ and OH-? Yeah? I can, can't I? And then those yield what? NaCl, right? Let's make the ions for, wait a minute, NaCl. Is it this? Or is it a solid? It's in water, yeah. Then it's like that. It's an ion because it's an alkali metal, right? And all alkali metals are what? Soluble. Okay? And then what's it make here? What are the other two things that are left? H+ and OH-. What do they make? So when I start canceling out spectators, what do I get? Really? H plus OH minus yield H2O liquid, don't it? That's the reaction for all Bronsted acids and bases. Try it with the next one. Try it with the next one. Okay? Try it with the next one. It is. Are these the same? They are, aren't they? Because I can divide all of this by what? 2. And if I divide all of this by 2, then what do I get? This reaction. It's the same result. Now I'm going to ask a question right now, and this is the point that I was trying to make. In acid-base reaction, what's made? Water is, isn't it? Okay? Because the salts are what? They're spectators, aren't they? Yeah. So we can do these, right? So as a chemistry student, once you figure this out, does this make the net ionic reaction for acid-base reactions a lot more fun? Yeah, I'm going to throw some complexities though, right? Because chemists always do. We mess with that, right? No, it's just because real-world chemistry is more complex than this. But when I have a good strong acid and a strong base, then this is what happens. Cool? All right? This is showing ionization of acids in water. Now, I really want to talk right now because we're there and we need this. And I really want to talk about strong and weak. Okay, I want to talk about strong and weak. Now, I might put acid in that phrase. I might put base in that phrase. I might put electrolyte in that phrase that would contain strong and weak, right? It's the same concept with all of those, okay? When I have a strong something, it disassociates completely, all right? Strong disassociates completely. The 1S disassociates. 2S one here, right? One disassociates. I think that's right.
That is right.
All right. So disassociates completely. And partially. I think because it has the pair of S's past the dis part, I want to put that in both places. Yeah.
So is this just for acids or is this also?
This is also bases, right? Strong acids, strong bases are strong electrolytes. Okay? So I want you guys, when you see the word strong electrolyte, what that means is that when I put it in water, it completely dissolves. You guys with me? So for every sodium chloride molecule that I put in, I get one sodium and one chloride ion. You guys with me? Now if I'm talking about bases, if I have sodium hydroxide, it's a strong base. And that means for every one molecule of sodium hydroxide that I put into solution, then I get one sodium and one hydroxide, right? Acids, yep, go ahead.
And is the strength determined by the number of bonds?
No, it's actually not the number of bonds between, okay? It's the attractive relationship between the two, okay? Right, so more sticky, less sticky, okay? And it's what water will stabilize, okay? And so if I'm looking up here on the left-hand side, then I'm showing a strong acid, okay? And what you see in that strong acid is that we have individual ions, okay? We have individual ions, and those ions are positively charged and negatively charged. So this is showing that, well, in fact, when I have an acid and it's a strong acid, then realistically what happens is H plus H2O yields H3O plus. All right, and this is called the hydronium ion. All right, and so a strong acid, the H plus actually mostly resides as this ion. Now, I will tell you right now that any chemist that I know would see those as the same thing. Okay, this is shorthand for this in an aqueous environment. You guys with me? Okay, so we'll see that written both ways. Now, so that hydronium ion is that H3 plus. When we put that strong acid in there, our Cl, for example, that we're using right now is Cl minus, and the chloride ion, and it disassociates completely. Cool? You guys with me? Now, if I come over here, this is showing a weak acid. Now, we used it in lab this week. We used glacial acetic acid, right? And when I put acetic acid in the water, then what I find is that it only partially disassociates. Most of it resides as the molecule, acetic acid, with the H plus on it. In other words, the acetic acid wants the hydrogen ion more than the water does. You guys with me? And in fact, there's a mathematical expression that we'll learn second semester. It's an equilibrium calculation, right? And all weak acids we're going to learn are used as buffers, and we can use them to buffer at different pHs. And there's actually defined constants, K values, Kas for acids, that will tell us how dissolved this is. So we can predict that mathematically before we ever make the solution. We'll know if I put this relationship of acetic acid in with the amount of water that I do, that it will buffer to this pH. And then I can shift that by adding the conjugate base. Okay? And so I can adjust my pH about a pH range of 2 units. Pretty easy. Okay? In other words, when I have a buffer and I have that Ka calculation, my weak acid will buffer plus or minus 1 unit from the pKa, right? Or the negative log of that. Now, I know I just talked in chemistry. All right? Maybe there's 1 or 2 of you up there that got that. All right? I don't expect you to get that yet. I'm going to teach you that. But that language comes to my mind right here. And so, because I want you to have that language, I'm putting it in your brain the first time, right? And then about 2,500 times later, you'll finally get it. Cool? All right? So, anyway, right now, what's the terms I want you to learn? There's 2 of them. strong and weak, okay? And then know that weak acids and weak bases are used to buffer, right? Cool?
Strong.
Strong are the ones that dissolve completely, right? We use strong acids in lab. Sometimes we use weak acids. It depends on what we're trying to do, okay? Now, there are some common ones that we want you to know, okay? That we want you to know them as strong acids. And those strong acids that we want you to know are HCl, HNO3, H2SO4, HClO4, HBr, and HI. In fact, we want you to know their names, and you would recognize many of these. You guys with me? How many people have heard of hydrochloric acid? Yeah, or what's another name for it? What's the common name? Muriatic acid. Okay, it's used to clean brick and masonry and those types of things. Okay, common. It's actually one of the safer strong acids. Right? In my mental brain. All right? Nitric acid. How many people have heard of nitric acid? A couple of you? What about sulfuric acid? Yeah? What about perchloric acid? That's one of the more dangerous ones. It works great to dissolve things. Can I tell a graduate school story right here with this one? Yeah, so in graduate school, we were trying to digest some carbonaceous material. Okay? We had some char that was made from subbituminous coal, and we'd done a gasification process on it, and we had put some lead in there and some other elements, and we could not recover the lead. We were trying to do mass balance. You guys have learned about mass balance, right? And so we knew how much we put in, and so we should have been able to get out the same amount of lead after we did the extraction, right? You guys with me? And when we were doing it, we couldn't get more than about 75% of the lead back, yet none of the stuff that we had trapped showed any lead in it. So we were looking for a better method to digest the carbon. And so we found a standard method which used perchloric acid. All right? And so the standard method that used perchloric acid was fairly easy to set up. We found the perchloric acid, we had it in our shells, and so we set up literally a digestion and reflux in the fume hood, following the method that was described. And now you have to know my graduate school experience. My research advisor, Dr. Manahan, he would come in about 10 o'clock. Now we started a lot earlier than that. We started I usually started about 6:30 to 7 in the morning. I was still a farm kid at that point. And Scott, who I did a lot of my work with, he would come in about 8 to 8:30. And so we would already be going. You guys with me? And then Dr. Manahan would come in, and he would always check with the two of us because we had a lot of joint projects going. And he would say, boys, what's going on today? And we would have a conversation about what we were trying to accomplish and how we were trying to accomplish it and all of those things. You guys with me? And we would bounce that off. He would give us feedback and tell us whether he felt we were headed in the right direction or if we needed to make an adjustment. Makes sense, doesn't it? And so we told him that we'd have trouble getting the lead, and we'd actually been discussing it this had been going on for a week or two, right? And he told us to go to the literature and find another way to get it. And so we did, and we set it up. It was already going. We were proud of ourselves. And as soon as we said that we had set it up and it was running in the hood there beside us, he said, boys, he said, we're going to continue this conversation on the other side of the building near Dr. Sharp's office. He just walks out of the lab. And so we're like, what's going on here, right? And so we go out the door, and he actually invites everybody else in the lab to go too. Okay? And we go around the corner to where Dr. Sharp's office was at, and we're in the hallway, and he said, boys, I want to tell you a story. So I'm telling you guys the story that he then told us, right? He said, I was at University of Wyoming, and he said, I was working in the Department of Energy Research Facility there, and we were working with coal. And he said, I needed to digest the coal, and he said, I found a standard method. And the standard method was using perchloric acid to dissolve the carbon so that I could do the analysis work that I needed to do. And he said, I got the experiment set up, And he said, I went then, he said, because I'd been consuming some coffee that morning, he said, I went to the bathroom to piddle. And he says, well, I was standing there piddling, and yes, that's the word he said, right? He said, the ceiling shook, dust came down, and he said, I'm standing there thinking, something curious is going on in the building. And so he says he leaves the bathroom, he says he goes back, and he says the corner of the lab that he was working in was gone. And I said, gone. And he said, well, he said it was in dust. All right? He said the explosion-proof fume hood was gone. He said the walls on both sides of the corner were gone. He said the ceiling was gone, and there was a big dent in the floor. He said, now, he says, Kenny, you've just had a baby. He said, I want you to just go on outside. And he said, if you feel that the wall is gone in the lab, he said, I want you to call emergency services. And I said, okay. And he said, Scott, he said, I hate to do this to you, but you are a single young man. You have no children. I want you to go into the lab and take that down. Right? And I need you to do that very carefully. Don't shake or agitate. Be sure and cool it down first. Go turn the heat off. Let it cool completely. And then take it apart. He said, now you don't have to do that. You can leave it running. He says, but I'm going to be working at home until you guys have either completed the lab or you have taken it down. Please let me know. And he walked out. Literally. He left. Perchloric acid. Now, why is it so dangerous? Because it oxidizes and forms gases like CO2, and it can happen very rapidly. Okay? Nitric acid can oxidize in the same fashion and can be used to explode. All right? Sulfuric acid, right, also is an oxidizing acid, and those acids need to be treated a little more. Well, they all need to be treated safely. Okay? But if you get those on you, then they digest you too. Okay? You guys with me? Yeah. So anyway, so I tell that story. Good story, isn't it? Yeah. That you should be aware of what you're working with. Safety is very important. Okay? We did note that it said in there that it could make an explosive mixture, but did you really worry about it? I mean, it wouldn't be a standard method if it blows up, right? That's what we thought anyway. So yeah, good lesson. All right, hydroiodic, hydrobromic, so all of those. Now here's the counter of those, the strong bases, the lithium hydroxide, the sodium hydroxide, potassium hydroxide. Now what do those all have in common? They all have alkali metals and they're strong electrolytes. Okay? So now these are actually slightly soluble, but they still provide an OH, which is considered a strong base. Okay? But the reaction's a lot slower. Yeah, kinetically slower.
Electrolytes on fold. So is electrolytes, like it says, strong electrolytes for strong acids and strong electrolytes.
Right.
So
Yeah.
that's not
And
really
these are more partially soluble, so I would. It's one of those weird things. It depends on if I put it with a strong acid, then it will dissolve more rapidly. Okay? So, anyway. But that's what that means. That yes, strong and weak are the same thing. Okay? For electrolytes, acids, and bases. I want you to connect all of those, right? Connect all of those. Alright? And then, down here we have some weak acids. Phosphoric acid, acetic acid, carbonic acid. We're going to look at that one in a minute. We're going to look at a couple of others of these: hydrocyanic formic acid, benzoic acid, ammonia, and methylamine, and those types of molecules. Okay? So all of those can accept protons and act as bases.
So you basically need to memorize that whole chart.
Yeah, at least a few of them. All right? Get to where you can use them in a working nature. Okay? Get to where you can use them. If you see OH combined with the metal, what are you going to think? It's a base, right? Right. If you see H in front of something, it's a acid, right? And then there is language. These up here, other than sulfuric acid, are all monoprotic acids. Sulfuric acid is diprotic. Phosphoric acid down here is triprotic, which means there's 3 acidic protons, and well, we'll learn about the weak acids and that mathematics next semester. Okay, cool? All right, because there's some relationship there that we're going to learn. So what does strong mean? All right, what does weak mean? Partially ionized. Cool, you guys got that? All right, concepts. All right, how about this one? I want you guys to do a total and net ionic reaction on that. Okay, just for practice. HCl, a strong acid. Yeah, disassociates completely. What's that? We already did this one?
Yeah.
Oh, oops. My bad. So I got that one. Oh, we already did this one too. My bad. I jumped ahead, didn't I? Is that all right?
Yeah.
Yeah, they're in here so you guys can see them. Oh, here's a cool one that's going on. What do you guys see here? It is a piece of coral. So what's coral made out of? Calcium carbonate, yeah. So limestone is also made out of calcium carbonate, yeah. So what are the, wait a minute. This is an acid, just to let you know that. It's in a strong acid. HCl works great for this, makes a nice demo. All right. What's in the bubbles? You guys want to hold on to that for a second? Do a little bit of chemistry?
Yes.
Okay. So here we go. Here's our reaction. You guys want to do the ionic equation on that? How you doing? Good? What if I tell you this is hard to do without additional chemistry? You guys ready for it yet? No? Do what? No, it's not actually combustion. No, it's actually just a natural thing. How many people drink soda pop? It's carbonated, isn't it? Is that the word they use? Yeah. It actually has what's called carbonic acid present. And so acids make things tart, right? They also use other acids like phosphoric acid in soda pop, just to let you know that. Okay? And citric acid and so on. Because tart things with sugar balance flavor, right? And taste wonderful. But when you open a soda or carbonated water, what do you get? You get a fizz, right? You get CO2. Okay? Now, carbonated water has the carbonic acid in it. That's what makes it tart and tastes tart to you because there's an acidic proton there, and H plus from that. Okay? But when that H plus is on, it makes the form of carbonic acid that actually is in equilibrium and becomes H2O and CO2. Now, believe it or not, this is even happening in your body right now. Okay? So, as our cells respire, what do they make? CO2, right? But we have an aqueous factory in there, right? And so carbonate plays a huge role in buffering the pH near 7, okay? And in fact, the slight change from pH in the muscle where it becomes more acidic from higher concentrations of carbonic acid, right? Because the CO2 is present in higher concentrations, to your lungs where the CO2 leaves, right? And when the CO2 leaves, what else do we make? Water. And so the pH shifts at that point to being less acidic. And when it's less acidic, then my hemoglobin grabs onto oxygen. You guys with me? So that's a pH shift related to this reaction. All right. We'll go into that a little bit more depth in a later lecture. Cool? All right. So this is the beginning on an understanding of that. All right. Biochemistry is where you really get it. All right. So now can you actually just substitute the H2CO3 with H2O and CO2? You can, okay? And make that one reaction. And then you can go through and cancel spectators. So what's spectating up there? Just the CO minus, isn't it? Yeah. So this is an acid-base reaction, right? This is an acid-base reaction, but it's not a strong acid this time, right? It's a weak acid, and the chemistry is a little bit different. So we can have acid-base reactions that behave a little bit differently. Okay. So here's your net ionic equation. Now, I have a question for you. Anytime I see a carbonate and an acidic proton is being donated to it, what should I automatically think? Anytime I see CO3, 2 minus, in an acid, what's going to happen? I'm going to make CO2 and water, okay? Anytime I see a carbonate and an acid is being donated to it, I'm going to make CO2 and water. Cool? So I'm giving you the hint. When you see that combined, well, in fact, anybody know any type of medication that uses this? Antacids, right? A lot of the antacids have carbonates, right? Alka-Seltzer or baking soda can be used as antacid, right? So, how about this one? Can you guys do the reaction, the net, total and net ionic reactions? Try them on your own. Try to break those ions down. Now, there's a bicarbonate ion there. What does bicarbonate mean? Instead of carbonate, what is bicarbonate? There's another name for it, it's hydrogen carbonate. So that's an ion that stays together, okay, in this situation. All right, HCO3 minus is hydrogen carbonate or bicarbonate, right? When I put the sodium in front of it, Na plus, right? And sodium bicarbonate. And then plus stomach acid, H plus CO minus. And so if I add this H plus to this, I make carbonic acid, right? H2CO3. And when I make carbonic acid, then it can dissociate into H2O and CO2.
With the H2O.
Yeah. That's what I would put on that. It's not on there up there. Oops. So for carbonates, what do we make? We make water still, right? But we also make CO2. Okay? Now if you start with a solid like calcium carbonate, then those solids remain in the reaction too. So then that's a little bit more complicated because of that. Alright? So guess what? Tums work the same way. Alright, and we've already done that. Actually, I think the calcium carbonate should still be in that one. Alright, how about this one? This is going to do the same thing our carbonates did. Okay, this is sulfites. Sulfites do the same thing as carbonates. Let's see if you can figure this one out. So I gave you the preview. Got 2 minutes. Got 2 minutes. How many people are taking that H2SO3 and expanding it right now? And then they're going to substitute in H2O and SO2 at the end of this reaction, and then do the ionic expression. We've done a bunch of these. I'm letting you guys do them. Is that all right? What's the hardest part of this? It's making ions, isn't it? Right? Because once you get a total ionic, it's easy to cancel, isn't it? Right? Unless you've made the wrong ions or identified them wrongly. Okay? So you have to be able to recognize a sulfite or a bisulfite or those types of molecules, carbonate or bicarbonate. And so you have to be able to recognize them and assign the right charge and those types of things. That's the difficult part in my mind. So, but this stuff's kind of fun, isn't it? I mean, in comparison to some of the other stuff we've done. Yeah, once you get the hang of it. Yeah. So I'm done for Friday. We'll go back and do a couple more of these next week. I'll just come in and make you guys do them. And we'll kind of finish up the net ionics and start into oxidation states. And formally teach something I've already asked you to know.